Okay, welcome back. Let's begin lecture. We're going to be talking about the outer parts of the solar system today, asteroids and comets. But before we do that, I want to remind you that if you have difficulty with your iClicker, and for instance, I got a message over the weekend from a student saying, Dr. B, my iClicker, I don't seem to be getting any points. Can you help me with it? And if you have any kind of problems like that, please come up and sit with in the front row by where Brandon is, and he can help you with your iClicker. It sometimes is a pain in the neck getting it registered and stuff, but we've described how to get registered any number of times in this class. So the same thing with masteringastronomy.com. We're almost halfway through the semester. If you're not registered with masteringastronomy.com yet, it's, I don't know, it's looking tough. Okay, let's continue and talk about Chapter 9 concepts. The asteroid belt is an interesting place. Just a few basic specs about it. The largest asteroid is Ceres. It's about 960 kilometers in diameter. It's not a perfect sphere. Its orbital distance, 2.767 astronomical units. So it's out there past Mars, which is about 1.5, but it's not quite as far as Saturn. It's part of the asteroid belt. And the asteroids are generally not round. There's a lot of cratering. And the way to think about an asteroid is they're, like for instance, this one down here. Let me get my cursor. Come on, cursor. All right, here we go. This one down here, it looks like a shoe, kind of, I guess, or a foot, somebody's foot that's in a cast. Anyways, it doesn't look like a sphere. Most of them are not, but you can see they have a lot of craters on them. So they're in an area where there's a lot of small particles that will produce, a bunch of little craters and stuff. Sometimes they'll fracture. I mean, this one up here has obviously been fractured, so into smithereens. It's been blown apart. The Ceres shape is this gray sphere, or this gray figure. It's elliptical. It's not exactly spherical, and I made it to represent this set of measurements for it. The major axis of this is roughly the distance from Orlando to Nashville. Here's another way to look at it. If you think about Ceres being a circle, this is about where Ceres, this is the shadow Ceres would cast, centered on O'Hare Airport in Chicago, and basically casting a shadow all the way down here in Atlanta and all the way up here in Fargo, North Dakota, and almost all the way to Ottawa, Ontario. So it is fairly biggish, almost all the way down here. There's Dallas down here. And entire states are underneath this. So Ceres is a pretty big piece of, well, for our considerations. In the solar system, it's pretty small, I guess, but for our purposes, here's some enhanced high contrast views of Ceres from the Hubble Space Telescope. And you can see that there's stuff on there. We've been looking at this for a while, trying to figure out what this stuff is, this bright spot. We don't know what it is. And so people are trying to figure it out. Here's Vesta. Here's another big one over here, Vesta. This is the fourth largest of the asteroids. And this is not exactly a close-up view, but Now, the reason the asteroids are so small, and a lot of them, they're basically the kind of stuff that you would have found 4 billion years ago when the solar system was forming for the first time. But they never got the chance to form into the core of a gas giant like Jupiter or into a separate planet like Earth. You know, Earth is mainly rock and metal. The reason for that is orbital resonance, which is something I asked you to read about over the weekend. This is figure 9.4. This is probably the most important figure in that chapter, so let's take a look at it in detail. The asteroids that have an orbital resonance with Jupiter experience periodic nudges. All right, so what that means is right here is Jupiter's orbital period, okay? And the vertical axis here shows you the number of asteroids. Now, there's a pile of asteroids right here, a small pile that orbit with Jupiter. If it has the same period as Jupiter, it has the same semi-major axis. Therefore, it's on the same orbit. But between Jupiter and Mars, there's a big pile, gigantic pile, thousands of asteroids. But then there's these dips, all right? And these dips correspond to places where the orbital period is a number fraction of Jupiter's. So for instance, this one right here where it says 1/3, okay, that means that, and this is kind of a very narrow dip in the accumulation or the distribution of asteroids. There's no asteroids right here. Okay, so make a note. See if you could draw a picture of this in your notes. I mean, it's in your textbook. Make a sketch of it, and let's just emphasize this gap right here, 1/3, the 1/3 gap, the 1 to 3 gap. What that means is for every one orbit of Jupiter, the asteroids, if they were at this position, they would orbit 3 times. They're in closer, so each orbit is faster. And at this particular distance, this particular period, they go around 3 times for every one Jupiter. Now what that means is that every 3rd time around, Jupiter's out there in the same position. Jupiter's big enough and close enough to give it a little nudge toward itself. Okay, so it gets a little bit of a nudge gravitationally towards Jupiter. Now the main thing that it's interacting with is the SUN. But Jupiter is big enough and close enough that this part of the asteroid belt is empty. There's nothing there, not hardly. I guess there's probably a few. And this is important because it is an example, Sarah, of how Jupiter clears the inner solar system. So make that an emphasis, Anton, in your notes. Okay? Jupiter is clearing the inner solar system of asteroids, comets, and in general, all the rock and gas and dust that were present in the solar nebula at the beginning and are not here now. Now, we still get comets. It hasn't completely cleared everything. So make a note to yourself. Jupiter hasn't finished yet. Saturn, those are the 2 big sweepers. Earth sweeps a little bit. Every time we absorb an impact from an asteroid or a comet, we've swept. We've done the same thing that Jupiter does in spades. So Earth will sweep, the moon will sweep, Mercury will sweep a little bit. The sun sweeps a lot, of course, because comets, a lot of times, they'll get nudged right into the right orbit and zap, they go right into the sun itself. And the sun is so big that, it doesn't even feel it's not even a mosquito bite to the sun. Anyways, so Jupiter is clearing. It cleared this gap. They're zapped out of there. They're either sucked into Saturn after, continually. It's like somebody nagging you, like your mother-in-law, right? And they're picking at you and they're nagging at you. Now, most of you guys are young enough that you don't have a mother-in-law, but the concept is well known that if you get nagged, or you're, probably nobody in here has a bad mom, but I mean, moms can sometimes nag you worse than a mother-in-law. And if they nag you and nag you and nag you, like me nagging you guys about homework 2 times a week, just think if I did that, like every 3 days for a year, you'd get the message. And these asteroids have gotten the message. Clear out, right? And there's a bunch of gaps. Here's another gap. It's way depopulated. This is the 4-to-1 gap, 1/4. One orbit of Jupiter, 4 orbits for these asteroids, and it's mainly cleared out. Stuff will get perturbed and assume an orbit here that, like one of these, an asteroid from one of these big piles that's not getting a resonance. It's not an orbital resonance with Jupiter. These guys, they could be pulled out, or they can, get into a collision with another asteroid and end up getting shot into one of these gaps, but they'll be sucked out of that gap, the 1-to-4 gap, 1-to-3, all these relatively simple fractions. Look at this, 3/7. So that means for every 7 journeys around the sun, asteroids at this distance hook up with or get an extra tug 3 times out of 7 from Jupiter. Okay, this one 2 times out of every 3, right? And of course, here they're actually these ones are actually synchronized with Jupiter. These are called the Trojan asteroids. They actually live on Jupiter's orbit, a little bit in front of Jupiter and a little bit behind Jupiter on its orbit. And you can read about it in chapter 9. So eventually the nudges move the asteroids in some way out of the resonant orbits, and it leaves gaps. So emphasize in your notes, figure 9.4, really, really important. Let's take a little more close-up look at it. There's a nice little close-up. And they're not perfect, but here's two orbits of Saturn, 5 orbits of an asteroid. And actually there's another comet. It affects the orbital geometry. Another thing that we've noticed is that the rings of Saturn have similar resonances, but not with Saturn itself, but with moons of Saturn. So the rings of Saturn are cleared similar to the way that the asteroid belt is cleared. Okay, so here's an overhead view, and here are the asteroids that travel on Jupiter's orbit. The Trojan asteroids, they call them. So one of them's up here, and there's like 60 degrees, a 60-degree angle with Jupiter, the Sun, and the asteroid group for this one, and then another 60-degree angle over here for this group. So they travel on Jupiter's orbit because of the dynamics of because of the forces, mutual forces of Jupiter and the Sun. This is a stable point on Jupiter's orbit. So these guys are in resonance and they're stable. The main asteroid belt, the asteroids that are in resonance with Jupiter out here are not stable. So make a note of that, that they are unstable. Those rocky planetesimals, they couldn't form into a planet. Jupiter kept things stirred up. The entire asteroid belt is topsy-turvy enough that even if there was enough stuff there to make a planet, which there isn't, supposedly there isn't much. You could maybe make a small planet. It wouldn't. It just wouldn't stay together. Now, Earth was far enough away from Jupiter that, when it accumulated, it stayed together. It didn't get pulled apart by Jupiter. Mars, the same. Mars is pretty small, probably for that reason, that it's so close to Jupiter. Okay, so the orbital resonances prevent the accretion of all this stuff out here into a planet. But Mars is far enough away, yeah, you can get a small planet. Earth, Venus, Mercury, they all got formed up into a planet, but not this area here. Now, what that tells you is that this stuff in the asteroid belt, a lot of it, Charles, is leftovers from the very beginning of the solar system. Let me repeat that. This stuff in the asteroid belt, a good fraction of it, is leftovers from 4.5 billion years ago, the beginning of the solar system. It's been there the whole time. Okay, now there's interactions, and they'll collide and chip off fragments and stuff like that. But basically, the theory is that a lot of that stuff is leftovers from the beginning of the solar system, and that's kind of important. Here's another way to think about the asteroid belt. It's like hikers going through a forest, and they beat down the grass and all the plants and stuff, and they wear a path. Matter of fact, on campus here, you sometimes see it. But when they put up a new building, and they don't put up enough sidewalks, or they don't put up the right sidewalks, then students and everybody else will tend to walk in a certain direction from this door of the new building to the student union or whatever they're heading for, and they'll beat a path across the grass, and the grass will be beaten down, and you'll see all the rocks and the sand and everything like that until they put a sidewalk in. Eventually somebody will wise up and say, we need a sidewalk right here. Same thing with Jupiter. Jupiter is like the process of beating down that path. You can't really get a tree to grow on a path. You can't get a planet to grow in the asteroid belt. Okay, let me check something here. Okay. All right, let's continue. Now, getting back to this basic outline, many of the asteroids have fallen to Earth as meteorites. Now, this is good old NWA 7304, which we have talked about, and which we will talk more about. Quote from page 262, the asteroid belt was the only place where rocky planetesimals could survive for billions of years. So they never formed really into a planet. Sometimes they get budged out of their orbit by collision with some, another one, because they're in there gravitating with the other stuff that's nearby them, and they'll get nudges from Jupiter. So if something, for instance, gets nudged out of the 1 to 4 gap from Jupiter, it might collide with something a little closer in or a little further out, and then that thing that they collide with will maybe fracture or maybe get bumped into a different orbit and stuff like that. All right, so stuff like NWA 7304 we think are leftovers from the beginning of the solar system. So take a look at page 262 there. Now, I want to go over some orbital resonances with you. I believe I went over this with you last time. Did we look at this? Yeah, question.
Can you go back to the last slide for a moment?
No, I cannot. Get it off YouTube. Okay. Remember to make your notes just basic notes and then fill it in from YouTube if you don't get it all during class. I mean, when I'm on it. Did we look at this table? Io, Europa, and Ganymede last time? I can't remember. All right, go ahead. Let's take a look at this. Okay, and what I want you, I think we did actually. Where's my, yeah, that's, all right. Look at this one. Here's the orbital period in days. Now this is orbital resonance for moons of Jupiter. Now here's the orbital period, 3.55 days. And over here for Ganymede, it's 7.15. Now those guys are in resonance at about 2 to 1. All right? And this one over here, Io is roughly 4 to 1 with Ganymede. So it's, yeah, so there's all these kind of gravitational interactions. All right, let's take a look at Saturn's moons. All right, and I want you to sketch in this table. Mimas, Enceladus, Tethys, Dione, and Rhea. Now here are the radii. They're not that gigantic. They're fairly small. Here are their orbits. And here are the orbital periods in days. And what we're going to try to look at, I want you to especially have these orbital periods. Mimas goes around Saturn in less than a day. That's pretty fast. Enceladus, just over a day. So this is 1 day and, I don't know, 0.37. That's, I don't know, 7 hours or so, 8 hours. 1.88 days. And down here, Rhea, 4.5175 days. So now the radius and the orbit are not the main interest for us. What we're orbiting, what we're interested in are the orbital periods. So take a minute to copy down this table. And just jot it down into your notes. It's on the internet. You can look it up on the, good old planetary data sheet, planetary fact sheet page. And, and that'll be good. And on exam 2, which is, I guess, coming up after the spring vacation, spring break, exam 2, if I was going to ask you questions about this chiral, this table would be on the cover page. So don't worry about having to memorize this, but do worry about this task. If you have this table, Matt, do you know what to do with it? Do you know what it means? Anybody, I mean, you could teach an engineering student to memorize this stuff, so that's not that hard. But what, what's the meaning of this, Dakota? That's the thing that we want to, try to analyze, right? I see you're doing, Paul, how are you feeling? Getting there?
A little better.
All right.
But unfortunately,
Well, hang in there, my friend. Good days are coming. Alvaro, did you see the modification I made for you? Okay. Yeah, so this is the stuff that we're going to try to analyze. Now, I want you to look at those. Go ahead and take a look at this. Let's just do a little mental IQ test. Do you see any resonances? Any 2 to 1s or 3 to 1s or 4 to 1s? Look. Do you see any? Between any 2 rows. Raise your hand if you see one. What do you see? 2 to 1 with Dione. Is that right? You break out your calculator if you have one. Check to see, is it close to... Okay, so Rhea divided by Dione, is that really close to 2.0? How close is it? Who's got a calculator? What do you, yo, Dakota, what do you got? This is 1.65 to 1? Okay, so that can't be so that's not a 2 to 1. All right, but you're looking at, you're thinking of, what's your name back here? What? No, back here. What's that? Liz. Liz, you're thinking the right way. Drew, do you see something? What do you see?
2 to 1 between Tethys and Mimas.
Tethys and Mimas. Can you guys check this? 2 to 1. Tethys divided by Mimas. 1.99. Is that what you got? Okay, 1.99 is actually pretty good. All right, so make a note. Tethys and Mimas, 2 to 1. Tethys 2, Mimas 1, approximately. All right, so that's going to give them some tidal interactions and some heating. Anybody see anything else in here? Any other 2 to 1s? Let me see. What's your name again? Leland Carlson. Could. Okay, Leland Carlson, what do you see? Here, Dione and Enceladus. 2 point, yeah, that looks about. Can somebody check that? What's the fraction? Dione divided by Enceladus. What do we get on that? I kept seeing a guy back here. You're on your phone. You're not on your calculator, right? Yeah, all right. All right, who's slacking? Who's got a calculator out? Okay, so 1.99 for this one. Yeah, okay, I agree with that one. Go and slot that one in. Make a note of that one as a resonance. And I believe there's, let's see, let me just check something here. I believe I've got another animation here. This is the one that, Drew, I think this, did you bring this one up, Drew? Yeah, Tethys and Mimas. All right, so there's 2. And it's kind of cool. What this also means is that these moons have been in existence long enough to get synchronized like this. And in addition, you know, our moon has been in existence long enough that it's at exactly the right distance and exactly the right spin rate so that the same face of our moon is always facing us. So the spin period and the orbital period around the Earth are the same. And it didn't start out that way, I'm sure, but it has gotten to that point. All right, so a little bit more about meteorites. Here's 2. These are figures from your textbook. Primitive meteorites. These are the kind that are the leftovers from the solar nebula. So they're blobs of minerals, pyroxene, olivine, and so forth. Okay, they're now solidified. An example of a primitive. Let me get my cursor over here. Okay, an example of a primitive is Allen Hill's A77280. Right, discovered down the Allen Hills ice field of Antarctica. Okay, and so so we find meteorites like this on Earth. I mean, for example, this one from Allen Hills in Antarctica. NWA. Here's a second kind, and these are called processed meteorites. And we think that these ones are fragments of stuff that formed from the solar nebula. So we think that NWA 7304 is a fragment of a larger object. And so these two different kinds of meteorites, processed and primitive, a lot of times if we can see them as they fall, which isn't always possible, but sometimes it is, if we can see them as they come in, we can estimate where they came from. You know, because if they come in at a certain rate, at a certain angle, that means that they probably came from a certain region of the sky. And if that's, you know, if that's near Mars, or if it's near the asteroid belt, or if it's near Enceladus or something like that, we can figure that out a lot of times. All right. And so these meteorites that are you know, coming in from the asteroid belt, a lot of them, are basically budged out because of orbital resonance. So a lot of them, you know, are going to get budged out and end up inside Jupiter, but some of them get swept up by Mars, and those are the ones that we're looking at here. Now, Mimas is orbiting Saturn, and it itself has cleared a gap in the rings of Saturn, and it's called the Cassini Division, after the guy that first spotted it several hundred years ago. Here's the Cassini Division. In other words, the rings of Saturn, it's not like a plate, it's not like a ring, you know, it's not like a washer. It's zillions and zillions of little well, I shouldn't say little, boulders and little rocks, little fragments that to us look really, really thin and very pale. And we can see them from Earth with a decent telescope. You could probably see them from Earth if it's a good night with a pair of binoculars, although you might not see the details that we see in this. This is an image from the Cassini spacecraft of Saturn. But this division here, that's called the Cassini Division. And you know, here it is over here. Okay, that division. And Mimas is out past there. But just like Jupiter is out past the asteroid belt, but yet it clears different gaps in the asteroid belt, Mimas is out here, and we're pretty sure that Mimas is keeping the Cassini Division close to empty. But if you look at it closely, as the Cassini spacecraft has been doing for several years, you will see that the Cassini Division is not perfectly empty. There's still stuff in there. But look at all these tracks. Now, in the olden days, when I was a little shrimpy kid, or when I was a young student, an undergraduate student at Carleton College, Harvard of the Midwest, we had records, and that you put on a little circular table, and it would go around, and you put a little thing on it that would create sound electronically. Records, and made of vinyl. And this looks exactly like those records that have tracks. And between every song, there's a little gap in the record, you know, where the plastic or the vinyl is smooth. And so when one song finishes, it goes right to the next. Anyways, that's back in the days of, you know, like almost the days of Noah, when we had those things. And 8 tracks, 8-track tapes. You know, back in the 70s, you know, there were these things called 8-track tapes. And if you had one, if you had a big, you know, like a Cadillac, and, you know, Elvis probably had a Cadillac with 8-track tapes in it, playing Elvis tapes in Elvis 8 tracks in an 8-track player in his own Cadillac. Now that would be pretty cool. Kyrell, you got a question? Mimas is keeping most of the stuff out of there, but there's stuff that, you know, don't forget, there's all kinds. We never realized this until we had Cassini up there, the spacecraft Cassini. There's all kind of stuff happening in the rings, because these things are continually getting replenished. You know, there's things that are emitting water vapor, and that water vapor is, you know, filling some of these gaps. It is just amazing. Some of the rings are actually braided. It's it's very dynamic. Okay, so so my note to you is that this division is similar. If you look at it, you can see that it's depopulated, but it's not empty. And just like the asteroid belt is depopulated at 1 to 4, 1 to 3, 2 to 7, and so forth, but not completely empty, because stuff continually gets, you know, mussed and fussed and budged and bounced, you know, and trounced in and out of the different orbits and stuff. Question? They're in circular orbits, pretty close to it. But you know, the thing is, I should try to get an image. They found that some of the rings of Saturn are not perfect circles. They're braided. And they're braided because of you can't really see it in this image, but there are little teeny moonlets. They're big enough that they're not really a moon, but they're not really a ring particle. They're called moonlets. And they're in here, and they cause some of the rings to braid and twist around each other. It's pretty cool. So I'll try to get an image of that next time. But most of the stuff, yeah, circular orbits. And so it's just like, like how when you leave the ball game up at the stadium, and that, you're trying to, did you ever go to a ball game at the stadium? Well, so there goes that analogy. Well, for those of you that have been to a ball game at the stadium, when you leave after the game, there's these huge masses of people. And because of the way that they so incompetently set up the traffic, the foot traffic, sometimes you have to wait like 15 minutes, like 1,000 people, 15 minutes in this big clump of people before you can cross the street, over to the inner part of campus. So last time I went to a game, it was a real mess. Anyways, but once they get going, and once the cops say, okay, everybody come across now, everybody moves, And it's the same thing as this. All these things they're all moving in unison. Well, each, like this ring, this little teeny ring here is in unison, and these ones are close to being in unison. This bright ring here, unison. They're all, and the further out, the longer it takes. So these ones are a little bit slower out here. These ones are a little bit faster in here, stuff. But yeah, at each radius, they're all moving in unison. Comets. Comets, comets, comets. Comets. They look cool like this. Like they have, the word comet comes from the word for hair. I guess. And, in the olden days, here's the sun over here. In the olden days, they thought that a comet was a sign of impending doom, or the king was going to be overthrown or some stuff like that. In other words, superstitious. But we now understand what comets are. And they're basically big blobs of leftover stuff from the beginning of the solar system that sometimes come down close to the sun and where we can see them. Okay, reservoirs of comets. The Kuiper Belt and the Oort Cloud. The Kuiper Belt is here. You've read about it. You did some questions about the Kuiper Belt. And that's out past the orbit of Neptune. And then the Oort Cloud is like a spherical distribution. It looks like a donut here, but it's actually spherical. And it's way, way out there. So there's a lot of comets out here. Formally speaking, they're comets occasionally one of them gets bumped or nudged so that it makes a journey into the center of the solar system and then back out, taking many thousands of years to do that. But a lot of them are just kind of orbiting around at this level. Now we think that Jupiter has basically cleared a lot of the stuff out of the outer solar system into the Oort Cloud. And the Kuiper Belt comets are all in the same orbital plane, roughly as the rest of the solar system. And so we can identify a Kuiper Belt versus an Oort Cloud comet. And an Oort Cloud will come from any direction because it's a spherical distribution. So if something from this sphere gets disturbed, it can come in from the north. So like if this is the North Star up in this direction at the top of the picture, you could have an Oort Cloud comet come down, looping like that. But Kuiper Belt comets are going to come in along this plane of the solar system. And there's other comets and stuff around. So let's take a look at this image, 913. Oort Cloud, look at this, where's my cursor? Here we go. 50,000 astronomical units, about 1 trillion comets. And they have random tilts and eccentricities, so it's just like a mess out there. The Kuiper Belt, though, 30 to 55 astronomical units. And we think it's got about 70,000. But I'm sure they're trying to get more and more accurate counts on both of these objects, or both of these formations. And it says here, comets orbit in the same plane and direction as the planets because it formed at the same time as the rest of the solar system. So here's the belt of comets, the Kuiper Belt, from 30 out to about 55 AUs. Same approximate plane. And these are the really, really old ones. Okay, they've been out there since Kingdom Come. Now the newbie zone is the Oort Cloud. About 1 trillion comets, we think. And so this is from recent clearing operations in the inner solar system. So if for some reason a comet gets budged and in just the right way, it'll end up out in the Oort Cloud. And so NASA's statement is that the Oort Cloud is from about 5,000 AUs out to about 100,000 AUs. That's a good fraction of the distance to Alpha Centauri, the nearest star. Okay, so it's, the solar system, all these comets belong to our solar system. And our solar system extends out, maybe 100,000 AUs. That's ginormous. I mean, Earth is this little nugget of rock, third rock from the sun, at 1 AU. And to us, that seems like a huge, enormous distance, 500 light seconds. But these things are 100,000 times that. Okay? So this would be 500 times that. So let's see, 10 times that would be 1 million AUs. So this is about 50 million light seconds to get out to this level of the Oort Cloud, out that far. That's a long time, 50 million light seconds. I don't even know how many. Divide that by 300, somebody take a calculator. 50 million divided by 3,600. 50 million divided by 3,600, who's got it? 50 million divided by 3,600. Who's got it? It's going to be a big number. Who else has got it? 50 million divided by 3,600. What do you got? 13,888. Okay, so divide that by 24. 578, Drew? Oh, 570. Who else has 5? You got 578? Okay, so 578. So 578 light days. Right? So that's over a light year out to the edge of the. And you know, the nearest Alpha Centauri is about 3 point something light years out. So this Oort cloud is out there a ways. And so if you have a comet out there that does manage to come back into the inner solar system, it's going to be a long time before it comes back. It comes in, next time you see it's going to be like maybe 25,000 years from now. If it doesn't get, you know, blown up into smithereens by, you know, hitting some other comet or something like that. Check this out. Nucleus of Halleys Comet. Sweet. This is one of the first pictures that we ever got, fairly close to a comet. And you can see by looking at this that, you know, in a way it looks like a burning fiery furnace, but it's not hot. It's mostly ice. It's oblong. It's not even oblong. It looks like a piece of slag, really. It's got all kinds of, look at all these little fissures and crannies and bumps and stuff. It's definitely rough. It's not a potato. It's not like a fairly smooth asteroid. Boy, this thing is just, and you know what that's from? That's from the fact that every time it comes in close to the solar system, it gets all that thermal expansion and fracturing, and all the CO2 gets out, and the H2O and whatever gaseous material it's got gets outgassed, and it's kind of random. It's spinning too. It's got a spin, and so you look at it and you think to yourself, boy, this thing is a mess. It is definitely not. You know, it's not like a little billiard ball flying through space. It's, you know, so if Bruce Willis or somebody was going to land a spacecraft on this in order to save the Earth, yeah, they'd have a hard time, baby. That would not be easy. You might have to involve Chuck Norris to get this, you know, to get a spacecraft down on this, or Neil Armstrong. I guess he'd probably know how to do it. And here's some more of the recent comets. Halley's Comet doesn't go out that far, a little bit, you know, out here past Neptune. Tempel 1 and Wild 2, they're out there at the level of Jupiter. Okay, so they come around pretty frequently. Hyakutake, that came and made a visit back in the late 90s. And I believe I took some photographs of this actually when I was out in Montana. You could really see it well. But that's an Oort, I believe Hyakutake is an Oort Cloud comet. And these other ones, Halley and Wild 2, Tempel, those are, I guess those would be considered Oort Cloud. Halley for sure is an Oort Cloud comet. Or not Oort Cloud, Kuiper Belt comet. And Pluto's out there in the Kuiper Belt. So Pluto's been demoted from being a true planet, much to the consternation of many people. But it's considered a dwarf planet now, a Kuiper Belt object, a KBO. And Wild 2, for us, is an important comet. It's a Jupiter crossing orbit. It's out here in this family of comets that are associated with Jupiter. And for us, it is important because we sailed a spacecraft right into Wild 2. We've talked about it already on the Stardust spacecraft. So make a note about this comet hunting technology. This picture right here, this is the collection device. So we sailed this thing. Now here are the solar cells, these big rectangles. That looks like the space station. And this thing, it looks like a tennis racket. And it's not a whole lot bigger than a tennis racket. It's the collection device. And the interesting stuff didn't, you know, in these little rectangles filled with something called aerogel. The really interesting thing is something that hit on this aluminum the aluminum separators. And we're going to be talking about that in your homework readings. Here's a picture of Wild 2 right over here. So this is what the nucleus of it looks like when it doesn't have a big bright coma. And you can see that these things are really rough looking. They're definitely not smooth surfaces. They've taken a lot of abuse from thermal expansion and all kinds of mayhem. This is Comet Borrelli and Comet Tempel 1. Now, Comet Tempel 1 gives rise to meteor showers, and I believe Wild 2 gives rise to meteor showers as well. When these, so make a note, meteor showers. Meteor showers are nights, a few nights in a row sometimes during the year, when you'll see a lot of shooting stars if you're up past midnight. The best time to see a meteor shower is after midnight. And basically, it is like when a comet passes by, the comet's, continually losing mass. Sometimes quite a bit, sometimes just a little bit. So it's trailing this debris cloud. And when Earth passes through that debris cloud, all that debris that we intersect goes through our atmosphere and as a shooting star, a meteor. And those are the meteor showers. And so every year at the same time, I believe Wild 2 and Tempel 1, and I don't know, maybe Borrelli, I'm not sure about Borrelli, but I think these two, one on the left and one on the right, both give rise to meteor showers. Now, the best way to view a meteor shower is A, it has to be a clear night, all right? And it has to be the right time of the year. And you can always look it up, meteor showers. And then the other thing is to be up after midnight. And so if you're up after midnight, between midnight, true midnight, not daylight savings time, but true midnight and dawn, you'll be going right into the meteor shower, and that's when you have the best chance of seeing them. And I've seen meteor showers just amazing. And one time I was up in Montana watching the Perseid meteor shower at Montana State, and see there you can see a clear night many nights of the year. Most nights of the year, it's clear and nice in Montana. Unless there's big forest fires in the summer, sometimes they cloud up the skies. But otherwise, most nights of the year you're going to have clear. And the Perseids are like August 13th, August 11th, August 12th, in there. And I was up there watching it, the meteor shower, and I saw this really interesting thing. I was watching the sky. I was out on the lawn or the playing fields, and I saw this kind of reddish colored V going across the sky from the northwest to the southeast. And it was kind of V-shaped. And I thought, oh, that's a flock of geese traveling south, and they're so high up, they're catching the first rays of the sun. And then I thought to myself, wait a minute, it's not even close to, because it was like about 2 o'clock, and sunup wasn't until about 6. So I figured, okay, that's my first thought was, oh, a bunch of geese. And I thought, I have no idea what that was. So then I'm still out there looking at the meteors coming in, and here about an hour or two later, here it is coming back from the southeast to the northwest. I thought, now that can't, if those are geese, they must have changed their mind and they're heading back to the Northland. But so the next day, I went in. So I'm in the astrophysics program at Montana State. I'm writing my PhD in astrophysics. So I told my advisor the next day, yeah, Dr. Hiscock, I I saw this thing. It's like this red V-shaped thing. At first I thought it was geese, but then I realized it's going too fast and it's too high. And I think it was a UFO. Because I saw it coming back the same, opposite direction. And you should have seen my advisor. He was looking at me like I was some kind of a maniac from another planet or something like that. But then I was telling my buddies, my classmates, and they said, no, man, you know what that was? That was the SR-71 Blackbird. Because that summer, they had taken them out of mothballs, and they were doing training missions in the northwest part of the United States. And the SR-71 Blackbird, it's a spy plane. And it's the fastest plane ever built, supposedly. And it's famous because it goes so fast that the leading edges get red hot when it's at high speed, and that's what it was doing. And that's probably what I saw, the SR-71. But of course, that was never confirmed, so maybe it really was a UFO. I don't know. Anyway, so that's my UFO story and my meteor shower. And if you're ever out on a date with a lovely person, there's hardly anything more romantic than looking at meteor showers. All right, you're dismissed. There'll be some readings and web courses. Look for that, nothinginmasteringastronomy.com. Just some readings. You're dismissed.